Some of you who are paying attention, meaning presumably no flat earthers, may have noticed there was a grey line in the wrong place and that the skyline didn't quite match up on the left and at the right at the same time in the previous image. It's a pretty good match, but not all over at the same time, and didn't match the horizon, and the tower was slightly off. I've made some changes. It turns out I was right about having got the refraction wrong, but I was wrong about how I got it wrong. The problem was I was doing the refraction in the wrong place in the sequence. So I still have all the old code here, but I have added some lines. It still asks for polar and equatorial. It still has reality as the default values. It then asks for refraction, numerator and denominator. Their default values are 7/6. You can make it 5/4, you can make it 9/8, for a cold day and a hot day, very cold early morning maybe to some people, and a mildly warm day to people in Arizona. You can make it 8/1 if you want to. Make it 100/1 and see what happens. Then it asks for observer latitude, longitude as before, and it defaults to a position near Southport, which probably isn't where the cameraman actually was, but it's not far off. As for elevation, it now defaults to 7 meters. I did a line there. It still asks for the camera azimuth and tilt and converts to radians, as before. And it still works out the observer's actual position in the same way as before, but instead of working out his radius from the centre as all of that plus observer elevation, it now works out observer sea level as that. Observer actual radius is observer actual sea level plus elevation. Observer sea level refracted version is observer sea level times refracted numerator over refracted denominator, 7/6 r. Observer radius refraction is that refracted sea level plus elevation. We still work out the observer's x, y and z coordinates based on the physical, not the refracted version. Then ask for a target, latitude, longitude, elevation, and we still do the same calculation to work out the target's position, but again, sea level, actual radius, sea level with refraction, actual apparent radius with refraction. Having got that, we work out target position in reality, the vector in reality to the target, the vector rotated from using prime meridian, prime antimeridian and 90-degree east and west to using the observer's meridian, the observer's antimeridian, and points 90 degrees east and west from them. The next vector, which is the same thing but rotated to use latitude relative to the observer, and the azimuth and distance and elevation as before of that third vector. But we now have the midway sea level refracted, which is the average of the two refracted sea levels. This is not exact, so what? I mean, I could have worked it out with the midway between the latitudes. Close enough to the same result. Refracted vector y-coordinate, not the actual vector but the refracted vector, is the target's radius from the centre of the Earth with refraction, as in apparent radius, times the cosine of the actual distance divided by the apparent radius with refraction of sea level midway between the two, minus the observer's apparent radius, taking refraction into account. And refracted vector elevation is then has a tangent of that refracted vector y offset divided by the actual distance. It's not quite right, because that's where is that quite right? One of these lines isn't quite right, because it actually needs an arc sine in it to be really correct. But we're talking about really tiny angles. We're talking about, you know, one degree, 60th of a radian. It's close enough without the arc sign, you know? It would be the radius times the arc sign of that distance divided by the radius, which is going to be so close to the same thing that forget about it. Forget about it. Camera elevation with refraction is refracted vector elevation minus camera elevation, rather than just the actual vector elevation minus camera elevation. And now, rather than having to run through multiple times, it gives you the x-coordinate for both, the y-coordinate geometric and y-coordinate refracted in the output line. So now if I run it, I can say reality, reality, normal, normal, put in 99 for default, put in 999 for default, so that you can put in 0, 0 if you really want to be sea level, prime meridian and equator. Default. My bad. Latitude. The tower. Elevation. Now, the tower deck is at 120 meters and the tower top is at 158 meters. And I've been using those figures, but having switched from Google Maps to Bing Maps, I can pull up the Ordnance Survey map and get a spot height on the road in front of the tower, a little way north of it, of 11 meters. So I can add 11 meters. Instead of 158, put in 169. 13 squared. Extremely bad luck. Or 100 more than nice. There's your tower position. 0.0047565 left. 0.0039703 up geometric, but only 0.0036475 up refracted. Try a different location. .12 north. This is farther north than the tower, obviously. .115 west. We are on the east side of the Furness Peninsula, or on the west side of Morecambe Bay, depending on your point of view, and there is a spot height at a road junction on the A5087 of 11 meters, which gives me that position. 0.0183774 left, 0.00725661 down, geometric, 0.00719558 down, refracted. That is less angle down. Somewhere between the two is where it flips from refracted being lower to refracted being higher. That's not how things actually happen, but this program is not getting camera level exactly right. It's assuming perpendicular to a radius from the center of the Earth, which is not quite the same thing as level. So the result is that it pushes that in the refracted version, the foreground is pushed down and the distant ground is lifted up, which is reducing curvature, reducing apparent curvature, and giving you, more of the background seen over the foreground. If you want an extreme example of that, you'll be forgiven for not recognizing the coordinates, unless you actually live near there. That is Ward Hill in the Orkneys. 268 meters above sea level, 0.0750058 right, which is, quite a way off to the right, but it's still potentially in the frame of the picture. 0.0490134 down, geometric. See, this is to the -2, times 10 to the -2, times 10 to the -3 here. So this is, if you want one scale on which to draw this, 4.9 centimeters down on your giant wall painting, and this is 3.97 millimeters down. Bit different. And the refracted version here, 4.28, is 52, well, on that scale, 52 millimeters higher. So I did get the whole of the Blackpool Tower worked out, and at sea level, it's at, if we want to discuss it, want to describe it that way, 5 millimeters down, 5.05 geometric and 5.37 refracted. At the top, it's 3.97 millimeters up geometric, 3.65 millimeters up refracted, which is a difference of some tiny fraction of a millimeter caused by refraction, and the total apparent height of Blackpool Tower, if you wanted to plot this on a wall at that scale, would only be about 9 millimeters. And this thing, this distant hilltop down in the Orkneys, if you plot its geometric position and its refracted position on the same scale, the refracted is, did I say 52 millimeters? 62 millimeters higher. Refraction makes more difference to the apparent position of that very distant hilltop than there is angular height of Blackpool Tower from this distance, which can be seen